Good morning, good afternoon, or good evening. We are now on question 11 of the Step 3 2024 paper. And as with all of these videos, hopefully you've had a go at the question yourself and you've either completed it successfully and you're looking for other ways to have tackled the question, or you got stuck somewhere and you're looking for that little hint. As with all these questions, I've not prepared solutions before, so I'm hoping to give you my first thought, my first viewpoint going through these problems, and the mistakes that inevitably go along with it. We are on question 11, which is our first stats question. I particularly enjoyed the stats questions of the STEP papers when I completed these exams myself. And the thing to be aware is these will require knowledge of the further statistics material. This one is going to use ideas on the expectation of a discrete random variable. So if these are questions, if you do need a few more questions in your wheelhouse, I would heavily recommend having a look at some of the further maths statistics chapters. Not all of them will be relevant, but the expectations and the probability distributions are the most likely that come up. So let's dive straight in to this question 11. It started by giving us two facts, two summations. The first summation, well, both summations you can prove. The first summation is particularly pleasant to prove. Actually comes from expanding x plus 1 to the power of n and then setting x to be equal to 1 so that the bracketed version is 2 to the power of n, and when you set 1 in the binomial expansion of that, you get exactly the summation. And a similar kind of trick works for the other, and I believe the other is you differentiate that expression that you expanded there, which is quite a miraculous couple of ideas. If you do want to spend a moment to work through that derivation yourself, you're more than welcome to. So part I is first trying to show that condition on these binomial coefficients. Probably easier is to start with the right hand side with any kind of expression you're trying to prove. We want to start with the more complicated side and simplify to the easier side. So this, I'm going to expand out that binomial coefficient, which is defined as the factorial on the top, the other thing factorial on the denominator, and then the top thing minus the bottom thing for the final term. So that's r minus 1 factorial. So that these two terms on the bottom should add up to the total power, which in this case is 2n, which indeed they do. So I want to manipulate this. I'm aiming for a 2n choose r. So my denominator wants to have a 2n, an r factorial and a 2n minus r factorial. And we can see that that actually happens pretty quickly. The extra bracket we have is exactly cancelling with the highest term of that factorial. So that's left with 2n minus r. And if I were to make the denominator r factorial, I've put an extra r in the denominator. So I need to times the numerator by r. Because it's a show that I am going to make that just a little bit more explicit on the line above. So then that's r, 2n choose r, which equals the left-hand side as required. So a bit of a weird, a bit of a weird thing going on there. We're swapping something about that bottom part of that summation. Okay, so the second part of this section, we want to now show the sum. So we're now summing over the left-hand side of my expression and we're trying to turn it into something. Well, the first thing that I notice is this side looks very similar to one of these given results, but I've got a strong feeling that I don't want to use that given result here. That given result is getting rid of the summation. I don't want to get rid of the summation here. So instead, and the other thing to notice is the summation limits have changed. So it almost looks like we've ripped this sum into two parts. And I think that's going to be the useful idea here. So I'm going to start with the left-hand side this time. I'm summing from r equals 0 to 2n of that. And I'm going to swap this, well, I'm not going to swap it around. I'm going to rip it into two parts. I'm going to sum from 0 to n of that. And I'm going to add on the sum from n plus 1 to n of the same thing. So I've ripped it into two parts. And notice, oh, that's summing up to 2n now. This is exactly a copy of what I want it to be. But the other part isn't. So what could we do with the other part? The other part I can sum now from 0 to n using the thing I've just proved. So this is now 2n plus 1 minus r of 2n and 2n plus 1 minus r plus the sum. Most annoying thing about these problems is rewriting the sum carefully every single time. Okay, but how did that help us? I'm wanting to sum over, I basically want to change these limits. So when r is 0, I've started my sum at 2n plus 1. Is that right? So r equals, I really want to change this thing to be called a k maybe. So then I'm summing from k equals something to something of 2k choose k plus the other one. But I need to work out very carefully what the limits of this k are. So when r is, I keep pausing because when r is 0, this is 2n plus 1, which I don't really want k to be 2n plus 1. Because this condition does not hold. The above condition didn't hold when r was 0. So we need to kind of break off that case. So I only want this to sum from 1 to n, and I need to add on the r equals 0 case, which, well, is just a 0. So that was from when r equals 0. Because of this, well, really, I need to split it off up here, don't I? So let's, and here's a benefit of having done it on a screen. I can erase and change around, plus 0, and that's the case when r equals 0. Okay, so my limits now are slightly more pleasant. So when r equals 1, k is 2n, and when r equals n, k is n plus 1. So we're summing from k, and we're doing the summation backwards. The first term of this summation is the last term of this one. So we've kind of reordered the summation as well, but that doesn't really matter. But now these two summations are identical, they are using a different, what I would call a dummy variable, a placeholder variable. The R and the K are different, but they're just there as a placeholder. We're summing over them. It doesn't matter that they are different. Okay, that's part I done. So far, we haven't actually done any probability or statistics. We've just set up some quite interesting looking summations. Part 2, however, introduces a game. A fair coin is tossed 2n times. The value of the random variable is whichever is the larger of the number of heads or the number of tails. If both are shown, then we say that x is n. So the value of the random variable x is whichever is the largest of those. So the key fact that we're going to have to use here is the expectation is the sum over all the possibilities. So x equals something to something of x times the probability of getting that particular combination. Now, what can our possible answers be? Well, we can have a solution of n if there's exactly n heads and n tails. Or we're talking about the largest, we can go up to having 2n of either the heads or the tails. And here I'm looking straight away at this here, which very almost looks like the summation we're doing. So I'd quite like this part to match with that part in some way. One thing that I will do is to split off the x equals n case, because that is a little bit special. So probability that x is equal to n, well, of the 2n, I need to pick n of them to be heads and n of them to be tails. So the way I can get x equals n is 2 to the negative 2n, 2n choose n, which isn't a particularly pleasant thing, but if you look, that's exactly this part of my show that answer. So this is kind of being added on the end. Okay, well now let's say that x is greater than n. So now the probability that we get exactly x, well, of the 2n, I need to choose x of them to be heads. The rest, let's put that bracket in the right place. The rest need to be tails, and that's if we had more heads than tails, but you could add more tails than heads. So you've got the perfectly symmetric other case. So I can just put a 2 in front. One of these is from the heads being more prevalent, the other from the tails. Okay, and again I can manipulate that a little bit, and I am going to actually leave, although this looks a little silly, and I have actually got my power here wrong. This should be 2n minus x. Although I could cancel these 2's, I don't want to. And the thing there is x. One of the problems with talking through your problem, you often aren't focusing quite as much as you should on the calculations you're writing down. So now we get that the expectation of x is going to be the special one that we've split off, and we need to remember to times that by its actual value. So we get a value of n with a probability of that nonsense, plus the sum from x equals n plus 1 up to 2n of 2 over 2 to the 2n choose x. But now that summation is identical to the right hand side of the previous part, bar the 1 over 2n. Oh, I've lost the x has to pop in here. This x here needs to pop in. I mean, times by the value times its probability. So this is going to become, and I'm just checking the answer. The answer isn't writing with negative powers, so I'm going to stop writing with negative powers. Plus, this is 1 over 2 to the n, and that summation we can write as r equals 0 to 2n of r 2n. Choose r, and that's by part I. But that summation is something that's already given to us. So that's plus 1 over 2 to the 2n. That summation, as given right at the top, is 2 to the power of the thing that's sitting in the n slot, which in this case is 2n. So this is 2 to the 2n. Which I'm a little worried about because I want to factor out an n here, which I'm not getting. Oh, because I'm not using the first summation. I'm using the second summation, which has that extra r, in our case, the extra x that I want. So this is actually the 2n sits in front times 2 to the 2n minus 1. 2n is sitting in that slot. I am summing over the right things. I've changed my summation correctly. I've used up the 2 that I had. Oh, and yeah, I was a little worried that I wasn't going to cancel these 2 to the n, the 2 to the power terms perfectly, but this extra 2 here is exactly what we need. So this is equal to n over 2 to the 2n, 2n choose n, plus all the 2's cancel, plus n, and then finally writing it how they wanted us to write it. 2n choose n. That's required. Okay, lovely. Next up, we want to show that that thing decreases as n increases. Now, one thing I'm going to say from exam technique, this doesn't feel like in most other step questions that this should be its own part of a question. Normally this is like we had in part I, some kind of little condition that's then used to prove something else. So the fact that this has its own part means it's going to be a little bit beefier than maybe is previous, than maybe you would expect. So, how am I going to show this? I could rewrite it using factorials. Now that still doesn't particularly look very pleasant. We'd have 1 over 2 to the 2n, 2n factorial over n factorial. And we want to show that as n gets bigger, this thing gets smaller. And I'm actually thinking the most efficient way to do this actually feels like a proof by induction. Is it? No, I'm not going to do a proof by induction. That would work, I think, but I think the inductive step that would happen is exactly the step I want to do, and that's just showing the result. So I'm going to consider, I want to show this is decreasing, so I'm going to consider a particular term minus the next term. So that'll be 2n plus 2, 2n plus 2, and n plus 1. Now, if I can show that this is positive, this says the things are decreasing. So we're required to show this is positive. So that's my plan going on here. So only thing to do is to start expanding and trying to simplify. One useful thing is we can factorize common factors out. So this whole thing is going to equal to 2 over 2n plus 2. So that this is 4 2n factorial over n factorial squared minus, now the fraction out front's been taken completely, 2n plus 2 squared, sorry, 2n plus 2 factorial over n plus 1 factorial squared. So now what's common to everything here? I can take out a 2n factorial. I still have this 2 to the 2n plus 2 and an n factorial squared. So I'm left with 4 minus, left on this term is 2n plus 1, 2n plus 2, 2n plus 1. The rest of that factorial got expanded out to the front over, now an n factorial's gone out, so I'm left with n plus 1 twice. Now, is that bracket greater than 0? I would hope so. And probably the easiest way to show that is with a kind of algebraic division, which unfortunately is going to require a couple more steps. Soon I'm going to stop writing that thing out in front and just give it another name. So this is going to be minus. Now the denominator is n squared plus 2n plus 1. The numerator is 4n squared plus 6n plus 2. And I'm going to do something really silly with that numerator. I'm going to write it as 4n squared plus 8n plus 4, which is just 4 lots of the denominator, minus 2n minus 2. So I've kind of manipulated it to be the perfect form that I want it to be. So this is going to be equal to, don't really care what that is, 4 minus, I don't want another square bracket, but I do want a bracket, 4 minus 2n plus 1 over n squared plus 2n plus 1, which becomes, the 4's cancel, so this is going to be 2 lots of n plus 1 alpha over, well, I could have cancelled an n plus 1 here, but that thing is strictly positive, thus the sequence, it hasn't really been defined as a sequence, but we do have a sequence. The sequence 1 over 2 to the n, 2n choose n, is decreasing. We've shown the next term is smaller than the previous, so it's a decreasing sequence. So in particular, what is that saying? That's saying that this thing here is decreasing. This part of the expectation is decreasing. Okay, so how is the final part of the question going to bring all of this together? So now we have another game. In the game, you choose a value of n and you pay n pounds. A fair coin is then tossed, so this is like the previous. You win an amount in pounds equal to the larger of the number of heads and number of tails. So we know your winnings is exactly this x shown above. And again, we do have that condition that if they're equal, you win n. How should you choose n to maximize your expected winnings per pound paid? So our expected payout or winnings, our expected winnings is exactly what we've already got from above, 1 plus 1 over 2 to the 2n choose n. So we want to maximize. I shouldn't call that winnings really. That's my expected payout, is how much we get off the game, but my expected winnings needs to take into account that I've paid to join the game. So my expected winnings is this thing minus n, because I'm paying n every time just to play the game. So I'm losing out on n. So my expected winnings is that, and I want to maximize that. We know that without the n, this is decreasing. So without the n, you just choose n to be as small as possible to maximize that thing. But the n there is a little bit awkward. But if I want to maximize this, so I don't really. So one way is to differentiate it. I can call this f of n. I can try and differentiate it. Now, I really don't want to differentiate this function because it's incredibly unpleasant. I'm also thinking of how these functions are combining. We have some part which is decreasing multiplied by just a straight line. And when you multiply these, they wiggle around depending on which part is growing quicker and which part is decreasing quicker. So combining these together is likely to give, because powers and factorials almost always beat just the numbers. So I'm expecting that this function n looks something like the pink, and we want to find this maximum value here. Another thing that I could consider is splitting this into really two functions, n times what I can call g of n, because at least I know then that g of n is decreasing, so the derivative is always negative. Well, I can then, let's have a play with the derivative and see if it does anything nice. So if I differentiate this, differentiate the n, leave the g alone, minus differentiate the g, leave the n alone, and this thing wants to equal 0. Well, this g is really unpleasant. I definitely don't want to differentiate it. But I can say that as this g of n is decreasing, as g of n is decreasing, g dashed of n is always negative, and g of n, well, everything we're doing here is subbing in integers, which implies, I should get rid of that condition, which implies that f dashed of n is greater than 0, because it's something positive minus something negative, is greater than 0 for all n positive. So actually, f dashed of n is a strictly increasing sequence. So that's telling me that of the two components of this f, this bit is shrinking, but this part is always winning. As that gets bigger, it's getting bigger at a faster rate. So the n is beating the g of n component. And I'm pausing here because this seems to imply that we should pick n as large as possible. the expected payout is increasing as you put more money into this game. You get a better and better expected amount out. So that's your final answer. Pick n as large as possible. If you come across this game in the wild, you should put well, it's still random. And actually, this game can't make you lose money. You pay n, and the smallest amount of money you can win is n. So it's a very badly designed game. But you should put as much money as possible into it. Final thought then, before I close the discussion on this, is does that actually make sense for the story that's going on? If you only pay, let's say, £2 to play, you're tossing 4 coins, so you could win £2, £3 or £4 as its output. Is 2 the most likely? Yeah, 2 would be maybe the most likely, and then decreasing probabilities for the others. But if you were then to pay a lot, so you've got maybe 2,000 coins being tossed, well, yeah, that you would expect your payout to be a lot more, because you could win up to 2,000. Scaling out, of course, 2,000 is exceptionally unlikely, but you've got a chance to get a much higher payout. So it does seem reasonable that you should put more in, because the decreasing rate isn't decreasing at a sufficiently fast. Anyway, I'm therefore convinced by this answer. Of course, there might still be an error in there. I would recommend you check any of these solutions with official solutions as well. Hopefully that was useful. I really do enjoy these probability expectation style problems, and the rest of the playlist will have all the other questions in this paper. Good luck if you're attempting them.